Now the third question on today's document asks us to take the expression we got for the field contribution in a increment delta x on a x-axis at point x0, z. Here's the result that we got in the preceding video clip. We add up all these contributions and we get this expression, which just repeats this expression, except now we're summing it, and that is going to approach an integral. Our variable is going to be x. We have our delta x here. That's going to sort of become a dx. And everything else, the k prime I, the z, can all be factored out. And I only factored out the k prime here when I wrote this down. If we look at this, we see that we can factor out the I, z, and the j, none of which is involved in the integral, and we end up with a fairly simple integral, just dx over x minus x star squared plus z squared raised to the 3/2 power. We integrate that from negative infinity to infinity in order to get the field of an infinite line charge at a point in the xy plane. Now, the picture could be represented like this. Here we have our current. Here we have our field point. It projects down to the x-axis, projects over to the z-axis, and we see that the field is in the negative j direction, which will be the case here. This integral is certainly going to be positive, and there's nothing negative within the integrand. So the negative j, what we get is going to be a multiple of negative j. So we're going to get a field in this direction. A couple more things we can see. Z is a factor here, and if z only appeared in the numerator, that would imply a field that gets stronger as you move away from the line. But we have a z squared to the 3/2, which is essentially like a z cubed term, or at least a term that has something very much like a z cubed in the denominator, so that the field will decrease as z increases. Now we have to do the integral, and we didn't perform the integral. We're going to use a trigonometric substitution and some change of variable, some additional change of variable, and we're going to be able to do this integral rather easily. But the other thing we'll notice is we do have a right-hand rule. If we, and I'm going to have to step over here, if we put our thumb in the direction of the x-axis, then our fingers are going to curl around the x-axis in the counterclockwise direction, and that's very consistent with having a field up here that's in this direction. Also, since we could rotate this coordinate system any way we want to about the x-axis without changing the fact that we have current I running along the x-axis, this vector could really take any direction around that circle, so that we do have a uniform field surrounding that line charge.